So good morning everyone. I am Joel Conte, the PI for the NERI at UC San Diego Experimental Facility. And I would like to welcome you to our joint academia industry NERI workshop. We are very grateful for your participation and hope that you will enjoy the workshop and that you will get the information that you are interested in. We will also be very grateful for your input. We wish that this workshop could have been taken place in person, for real, but given the current circumstances, it was unfortunately not possible. The good news is that from what I can see in the Zoom count here, we have over 90 participants at this point. It's the largest number that we ever had in our past workshops. So a few general housekeeping items here. The workshop slide, all the presentation can be downloaded from the Google Drive, and you should have received a link from an email that gives you access to the Google Drive. For any problems or technical difficulties, please contact Dr. Kurosh Lotfizadeh, who has played a big role in preparing this workshop. And Kurosh, maybe I will let you say a few words at this point.
Thank you very much. Good morning, everybody. Thank you for participating in our workshop. We greatly appreciate it. Yeah, just a few items to note. All the attendees are automatically muted by default, just so we don't get too much crosstalk. If you need any assistance or if you want to ask us a question, please feel free to use the Q&A section in the Zoom program, or raise your hand and we can send a chat message to you. If you have any problems, if you get booted off, or if you have difficulties connecting, or if anything's not showing up properly and you just need some help with anything, feel free to email me. My email address is on the screen right now. Later on, just a couple of other quick words. Later in the day, we're gonna do a quick poll, and we're gonna gauge some interest in our breakout sessions for tomorrow. So just want to give you a heads up that in a short while, we're gonna do a poll and get your feedback on something. Thank you.
Great, thank you, Kurosh. So now the workshop objectives. So what we would like to achieve through this workshop is promote academia industry collaborations and identify high priority research needs, especially some that could take advantage of the upgraded shake table facility that we will talk about in the next presentation. We'd like to give you information about our experimental facility, and we'd like to, through the breakout session that we will have tomorrow, like to identify and formulate grand challenge research needs in earthquake engineering to advance the field, and also help you who will be writing research proposal to NSF, for example, help you to get as much information as you can get to prepare competitive proposals. And we'd like to brainstorm about example use of our upcoming upgraded facility to resolve part of the grand challenge that we will be discussing. So a few words about the agenda. So after this introduction, I will present, the capabilities of the NERI at UC San Diego Experimental Facility. Then we will have two of my colleagues, Professor Jose Restrepo and Tara Hutchinson, will talk about highlights of recent project conducted on the LHPOST. Then we will have a number of keynote presentations, 5 of them, 4 today and 1 tomorrow. We have Professor John van der Lind who will talk about building structures, Dr. Sisi Nicolaou about geostructures, Dr. Anthony Sanchez about bridge structures, Dr. Craig Davis about lifelines and utilities. I will provide a few concluding remarks. On both days, we have reserved some time in the afternoon from 2 to 4. You can get more information about this on the agenda. We have reserved some time to answer questions and provide some advising on future projects. We call this office hours. Tomorrow, we will start with a virtual walkthrough of the construction side of the LHPOS 6. We are going to call our facility LHPOS 6 once it is up and running with 6 degrees of freedom. Since when we have the workshop in person, we have a nice tour of the facility. You can see the real thing. We tried to create a virtual one. Then we will have Mr. William Holmes will present on project pre-planning and technology transfer. Then we will have breakout sessions, 10 groups for, let's see, from 9:15 to 11. And then the moderator of the breakout session will come present a very brief summary, and it will be hopefully a very healthy and good discussion. And then we'll have concluding remarks. So now I will start the first presentation here. Give me 1 second. Okay, so this presentation is about the capabilities and the description of our large outdoor shake table facility. So I will probably I will talk still about the 1 degree of freedom shake table so that you can appreciate the change that we have to make to convert it to a 6 degree of freedom. So I will talk about both the 1 degree of freedom version and the 6 degree of freedom version. I'll show a few small movie about past landmark experiments, talk quite a bit about the current 6 degree of freedom upgrade of the LHPOST and the new research opportunities that will be made possible. So the shake table facility is located not on the main campus, but 10 miles east of the main campus and 16 miles from San Diego International Airport at a field station called the Englekirk Structural Engineering Center. Let's see, I'm trying to get the zoom here. Yeah, okay. So this is a drone's view of the facility. You can see that the yellow plate is the shake table. We were testing at the time some electrical pole with transmission lines. We also have a soil foundation structure interaction facility there with 2 refillable large soil pits on each side of a large reaction wall. We have the hydraulic power system building that is containing all the hydraulic power supply for the facility. We also have a unique blast impact facility that makes use of servo hydraulic and makes use of the same hydraulic power supply as the shake table. The site is accredited through the International Accreditation Service, which means that over more than 80 countries in the world, the tests that are produced at this facility are accepted with no questions asked. So we were part of first the NEES network funded by the National Science Foundation. NEES stands for Network for Earthquake Engineering Simulation, from 2004 to 2014 for 10 years. And then we are now part of the NERI. NERI stands for Natural Hazard Engineering Research Infrastructure program funded by NSF as well. So from initially 2016 to 2020, but NSF is in the process of renewing NERI up to 2025. Here we have the UC San Diego team, but here we have pictures of everyone. So I'm the PI. There are 4 co-PIs, Tara Hutchinson, Gilberto Mosqueda, Benson Xing, and Lely van den Einde, each responsible for different aspects of the site. As you can see, Professor Jose Restrepo and Enrique Luco are senior personnel. They were the first and second PI of the site, and I'm the third one. Then we have Kurosh Lotfizadeh, acting site operation manager. We have Darren McKay, who is a research and development engineer, shake table operator. Robert Beckley, IT manager, and Alex Sherman, site foreman and development technician, and Jeremy Fitcher, development technician at all. Those of you who will come and work at the site, you will of course know these people and work with them. So the objective of the NERI at UC San Diego experimental facility listed here. So our vision is rooted on 3 critical needs for advancing the science, technology, and practice in earthquake engineering. There is need for much more research to understand better the system level behavior of civil structures, from the initiation of damage all the way to the onset of collapse. And then experimental data about system behavior is sorely needed because it is needed to develop, calibrate, and validate computational model that in the future will allow us to progressively shift away from our current reliance on physical testing to model-based simulation for design and assessment of civil structures. Finally, large-scale shake table testing are the ultimate validation test for new concept about seismic retrofit method, protective system, new material, component system, construction method to protect the civil infrastructure from earthquakes. When we designed the facility in 2001 to 2002, the key objective was to be able to reproduce, to develop a shake table able to reproduce accurately large earthquake ground motion, especially those produced by near source ground motions. Since we have a mild climate, we could do it, build it outside. So we have no height limitation, which allows us to test specimen that could not have been tested in the largest shaking table in the world at the Defense, for example. Many of our specimens could not have been tested there. So the facility was built in 2002 to 2004, commissioned on October 1st, 2004, as part of the NSF NEES network again. Since then, we have conducted about 34 major research and a few commercial projects in 15 years of operations since we closed on October 1st for the upgrade, October 1st, 2019. Many of the specimens tested consist of buildings made out of reinforced concrete, precast concrete, reinforced, unreinforced masonry, metal and light, steel, wood, timber, but we also have other type of structures like the wind turbine that you see here, and geostructures such as soil retaining wall, underground structures, tunnels, and so on. This slide here gives you a good rendering of the shake table facility. You see the large reaction mass here. Actually, I say large, it's 4,500 tons. It's actually relatively very light. If we had soft soil, for example, at the site, it would have to be probably 15, 20 times as big as what it is here. We took advantage of the soil stiffness and the radiation damping to have a light reaction mass, which helped us to lower the cost. But you see here that, so this facility was designed as a 6 degree of freedom shake table system, but built only as a 1 degree of freedom to accommodate the budget at the time. You see a picture here of the 1 degree of freedom version of it with 2 longitudinal actuators. You see the size of the platen, 7.6 meters by 12.2 meters, 40 feet by 25 feet. The salient characteristics of the table are the stroke plus or minus 75 centimeters. A very important parameter, the peak velocity, 1.8 meter per second, which requires an incredible flow of oil to feed the actuators, like we will discuss more later. You can see the peak acceleration for the bare table approaching 5G, 1.2G when we have a 400-ton rigid payload. The frequency bandwidth 0 to 33 hertz. The maximum horizontal force, this is a number that we will use to compare with the upgraded version now. So 6.8 meganewton or 680 metric ton. And the vertical payload capacity, 20 meganewton, with a very large overturning moment capacity of 50 meganewton meter. So to summarize, right, our shake table provides the ability to simulate near source earthquake ground motion, which involve large acceleration, velocity, and displacement pulses, allows testing of densely instrumented, large or full-scale structural specimen. And also when we use the shake table in combination with we have two large soil boxes that we'll talk about, we can also test geostructures, large-scale model of geostructures. We also have some basic capabilities for hybrid shake table testing. And in terms of education, this is an amazing tool from kindergarten to graduate school, and also for news media, policymakers, infrastructure owners, insurance, and the general public about natural disasters and the need to develop technologies to prevent these disasters from becoming societal disasters. So now let's go and look at the component of the shake table, right? First, the LHPOS, so 1 degree of freedom, and then it will allow me to explain to you the changes that we are making on the table to convert it to 6 degree of freedom. So here you have the reaction mass. Initially, we had 6 pressure balance bearings that in 2009 were already replaced by 6 vertical actuators, but ported with a very small servo valve so they could not be used dynamically until we will reopen next year. You see here one of the longitudinal actuators. You see 2 hold down strut. They are nitrogen filled tubes that apply a downward force, applied a downward force of to pre-stress the platen against the vertical actuators to give the overturning moment capacity. Appreciate the size. You see the length of the reaction mass, 33 meters, width 20 meters almost, the largest depth 8 meters. So here you see the platen, you see the longitudinal actuators, you see the 2 hold down strut. As part of the upgrade, we are going to need a 3rd hold down strut. You see we already had the plates here that the saddle blocks are ready to receive it here. We see a view from underneath. So when we move the platen, it moves on top of the vertical actuators through these wear plates that are represented in pink here. As part of the upgrade, we have to replace these wear plates with much larger ones, since now the table can go also in the transverse direction. And these gray plates that you can see here, they are the pressure balance bearing that are on top of the vertical actuators. You see here a picture of the hold down strut. So they applied a very large downward force of, you can see 200 metric ton. The weight of the platen is for the 1 degree of freedom was 145 metric ton. So we have 2 gigantic force of 200 metric ton, one at each end of the platen for the overturning moment capacity. You see here the horizontal actuators. So we had 2 for the 1 degree of freedom. They can push more than they can pull, but since we have 2, so they can, if you add these 2 numbers, you have 6.9 meganewton of push and pull of the platen. Each of these longitudinal actuators is equipped with 2 very large servo valves, with a very high flow of 2,500 gallons per minute, each of them. That's what is needed to reproduce the peak velocity, peak ground motion velocity of 1.8 meters per second. So this is one of these servo valve, gigantic. It's 4-stage servo valve. Those of you who are interested in servo hydraulics, you can see here the 4 stages. The spool that we can see here inside the sleeve for the 4th stage is gigantic. It weighs 320 kilograms. And you see that's where we receive the high pressure fluid at 3000 PSI. It arrives in this cavity here, and when the spool moves to the left or to the right, you can see these port windows. Then they would port the fluid either to the left or the right of the piston in the rod, and then the rod would either extend or retract and push and pull the table. So this is a picture of the vertical actuators that we already acquired in 2009. So they have a capability of moving plus or minus 5 inches, but we never used this capability until now because they were ported, you see, with a servo valve of 15 GPM. So no, we had no dynamic capability, but now we are going to port them with a servo valve of 5,000 GPM. Huge servo valve. You can see here the pressure balance bearings, that gray plate that is interfacing, that is connecting to the wear plate at the bottom of the platen. And you see the oil coming in these channels here, radial and circular. And there is a seal on the outer circle to contain the lubrication and the oil. Here, just to show you how, the hydraulic power system that we have when we want to reproduce an earthquake. We cannot rely on direct pumping from pump only. It would take many, many pumps. We have only 2 of them, 2 very large ones. You see the flow of the pumps here. And then we have a hydraulic, an accumulator bank, 50 bottle of 50 gallon each to 2,500 gallon. So basically there is nitrogen, they are filled with nitrogen. There is a piston at the bottom, and we can bring some oil at the bottom of each bottle. We can occupy up to 20–25% of oil. So we bring oil until the nitrogen pressure reach 5,000 PSI. When in idle situation, the nitrogen pressure is 3,000 PSI when the piston is at the bottom. So we pressurize oil in the accumulator bank, and when we want to reproduce an earthquake, we release this oil, we blow it down through blow down valve. We have 2 now. In the new system, we'll talk about it, we're gonna need 6 of them. And so the oil goes to, through large pipes, goes to the actuators, and then returns to a surge tank, a very large surge tank, which was designed to be large enough for the upgrade to 6 degrees of freedom. So we do not need to change that. You will see that we have to completely change the accumulator bank for the 6 degrees of freedom upgrade, and the pump, acquire 2 more pumps. So here, this was during commissioning a long time ago in 2004. So you can see how it works. You could see a view from underneath here with the nitrogen-filled cylinders. You see here a few words about the reaction mass. This is just after its completion in 2003. We did some forced vibration testing by using large eccentric shakers. You see one of them there, because we wanted to understand the dynamic characteristic of the reaction mass embedded in the soil at the site. So we had instrumented the reaction block and the foundation of the building and the foundation of the blast facility. And this slide is important because it shows you the frequency response function of the reaction mass of the block. So when we when both shakers at both ends were in phase and applying force in the east-west direction, showed by my cursor here. So the horizontal displacement at the top of the reaction mass, the blue curve here, as a function of frequency, and with the forcing function applied, scaled to the maximum force that the actuator can produce. Of course, the shakers could not produce this force. Later on, when we had the actuators, we did a test of linearity, and everything behaves quasi-linearly. In other words, we could scale the frequency response function from our test with the shakers, scale them up, and get the same frequency response curves as we got when we were using directly the actuators acting on the reaction mass. So you can see here that we have a characteristic frequency, so a natural frequency, so to speak, of the mass in the soil at about 10, 11 hertz, but it's a broad peak. There is a very high radiation damping, about 30 to 40%. And look at the deformation, a quarter of a millimeter. Very, very, very small. And this is same thing, but for the vertical displacement at the end of the reaction mass, since we have rocking, right? When we excite this horizontally here in the east-west direction, we have translation and rocking. So the vertical displacement, 0.15 millimeters. We also did some tests in the north-south direction. And this is published, those of you who are interested in this. Let's say now a few words about the MTS Three-Variable Controller, the 469D that was used on the LHPOST 1 degree of freedom and will also be used in the upgraded table. This is a controller that is used in all large shake tables manufactured by MTS. I should have mentioned early on that the design of this facility is a joint effort between a team of professors here at UC San Diego and MTS Systems Corporation for the initial design and now also for the upgrade. So this controller is a linear state variable controller, the three-state variable controlled by this TVC, stands for three variable controller, or displacement, velocity, and acceleration. We can choose the mode. It basically tells you which signal are you going to provide to the controller as a user. Most of the time we provide acceleration signal, earthquake accelerogram that we want to reproduce. And this controller has special features to compensate for the various sources of signal distortion due to linear dynamics or to nonlinear dynamics. And the options are different if you want to reproduce harmonic motions or broadband signal like earthquake record. The one that we use the most when we reproduce earthquake records are the adaptive inverse control AIC and the online iteration OLI, which is an iterative signal matching technique. So on this slide here, it's a lot of technical information, but I think some of you probably are interested in this. So just a few words. You see a block diagram of the TVC part of the controller, the basic TVC part for 1 degree of freedom LHPOST. You see a reference generator where you bring your signal, typically the acceleration, and then the reference generator will integrate to get velocity and displacement and differentiate again to get the jerk, the third derivative of the displacement. And all these signals are used in a feed-forward way in the control loop. So there is a feed-forward gain, a control feed-forward gain here. It gives a lot of flexibility to shape the transfer function of the shake table system. And then in terms of feedback signals, of course, we measure the acceleration feedback, the displacement feedback through the LVDT associated with the longitudinal actuators. And then internally, the controller computes the velocity. But all these three signals are not just measured. They are measured and then they are recomputed by considering that at low frequency, the LVDT produce the most accurate signal for displacement, and then at high frequency, the accelerometers provide the most accurate measurement. So they are hybrid signals that are reconstructed to get the best possible estimate of the real the true displacement, velocity, and acceleration. And there is the feedback, the force feedback, the delta pressure feedback coming from both actuators that is here. So the control loop, as you can see here, it's closed on the displacement. You see there is the target displacement here, and there is the feedback displacement. Compute the error, the difference is the error, and then this is an important control gain, right? The proportional gain here that multiplies the error signal. And then there is also a feedback, a force feedback in the loop, in the control loop. And then this produces a signal that is sent to the servo valve. So the output of the controller is a signal to the servo valve. When we go to a 6 degree of freedom system, every degree of freedom is controlled with that same scheme that you see here. So when we tune the controller for a shake table test, if you come and do some test here, we will ask you to give us your earthquake records. For each of them, the shake table operator will spend some time tuning the table so that this ground motion record that you give us will be best reproduced on the shake table system, on the shake table. So the tuning process consists of 3 steps. The first step, the shake table operator iteratively keep changing the control parameters, the feed forward gain and the feedback gain, until the shake table is able to reproduce a random type motion that we call the white noise at an amplitude of root mean square about 7% G. So the shake table operator sees the signal on the screen, the time history, and keeps changing the gain until these time histories are reproduced pretty accurately, or until the transfer function that you can see here is as close to 1 as possible. Of course, it cannot never be equal to 1 because it's a very complex dynamic system. And you can see here an example, the black, it would be the transfer function at a certain stage of tuning. And then in the second step, the inverse transfer function of the shake table system is estimated as accurately as possible using the AIC technique, adaptive inverse control. Because now this AIC will be used when we go to the third stage of basically OLI, which consists of changing the drive file to the controller until the output on the table is as close as possible to the ground motion that we want to reproduce. So it takes a number of iterations. So we change the drive file, the command if you want, we measure what comes on the table, we subtract the two to have the error signal, we filter the error signal through the inverse of the transfer function of the shake table and add it to the previous drive file. And you can see that this way, we have here the root mean square error between the target signal and the one that is reproduced on the table. That error goes down iteration by iteration until you reach a point where it cannot go down further and it starts to increase again. So at this point, we would save the drive file for this point, and the day of the test, we use that drive file to reproduce the earthquake motion on the platen. So this is to show you the accuracy of the LHPOST 1 degree of freedom. You can see that here we were trying to reproduce an earthquake record from the 1994 Northridge earthquake. You can see the acceleration time history, the target in red and the one achieved by the table in blue. You see the zoom here, see very accurate. You see here also the achieved and target spectral displacement and pseudo acceleration spectrum. We are very proud of this. It's very, very difficult for such a large shake table facility to have such accuracy. So in terms of instrumentation, whenever we test, some specimen, we have a large number of channels. We have 12 nodes at 64 channels each, 768 channels. Some of them have to be used, for the machine itself to understand the response of the platen and so on and so forth, but still overall a very large number of channels. We will have a brand new data acquisition system. In the past we had 16-bit, but we will also, we just were awarded an MRI proposal from the National Science Foundation to update the data acquisition system. We will have a 24-bit analog to digital resolution, and we will have perfectly simultaneous sampling and not multiplexing. And we will have over 25,000 samples per second per channel available. Typically, we sample at 200 or 250 samples per second. So we have an inventory of instruments. You see accelerometers, displacements, transducers, string potentiometers, load jack, load cell, soil pressure transducers. We have GPS, a GPS system that allows us to get displacement time history in 3 directions at 50 Hertz with an accuracy of 1.5 millimeter. We have high-speed camera that are all synchronized with the sensor data. And in recent years, Robert Berkeley has installed a fully configured end-to-end live video streaming production with minimum latency and very high resolution. A large number of people can watch online, a test online. And we are on social media, YouTube, Facebook, and Twitter. We have calibration equipment that is needed since we are accredited. We need to very often calibrate our data acquisition system and sensors. This slide shows you a number of landmark tests or specimens that were tested on the shake table. You will see short movie about some of them from some of the speakers today. I will show a very few in this presentation. You can see a precast concrete building here, a metal building, a 7-story slice of a building. You can see a bridge pier, full scale, a retaining wall, a 5-story building with all non-structural component and system, and so on. And now I'm going to show you a few short movies about some of these tests. So this was a full-scale 5-story building, reinforced concrete, total building with non-structural component and system, first tested on base isolators, one at each corner, and then fixed to the platen to simulate fixed base condition. This building had 2 different types of facade, light facade on the bottom and heavy precast concrete cladding on the top. And every floor had a different utilization to simulate a real building. We had even an intensive care unit on the 4th story and a surgery suite at the top. And we had a fully working elevator and stairs. So that, for example, non-structural component would be very difficult to be available at reduced scale, right? So the need for full scale here was important. And now a short movie about, so every time there is an experiment, the research team already has created a model of the experiment before the test. They have their best prediction ready to be compared with the experimental results. Here we are comparing in red the experimental result, in blue the prediction. You see the finite element model on seismic isolators. And you have here the acceleration on the table, the shear strain in the isolators, the displacement at the 3rd and 6th story. And here the interstory drift ratio, the floor acceleration, floor shear, and floor overturning moment. And I'm going to play this here. During this test, the shear strain in the seismic isolators reached 150%. You can see that the blue and the red are pretty much on top. Okay, so yeah, let's focus on the blue and the red on top. Right? It's easy to predict because the response of the building, except for the base isolators, is linear. You can see here the total base shear versus the shear strain in the isolators. And now let me go back and play this again, because we were playing the same earthquake from Peru, 2007 Peru earthquake at Ica, at scale at 140% for the base isolated building and 100% for the fixed base. So it was higher for the base isolated. And if you followed the movie, so let me go back and play the movie again here. You will see that the beds, you know, in the hospital room at the top, for the fixed base, they were very disrupted. You see the fixed base, the bed are going to top over, while here they are just slowly rolling in the base isolated system. So here, this is the same building, now fixed base, and you will appreciate the nonlinear response. The slab on the third story, you see a failure mechanism of the slab at the column slab joint. Here, the rebars at the bottom of the column merging into the column were ruptured at the face of the column. So this kind of nonlinear response mechanism, you know, buckling of rebars, bond slip, shear punching, shear failure of slabs, bar fracture and so on, they are still very hard to predict reliably with computational models. Still a lot of research is ongoing to try to capture these failure mechanisms. We also have two large soil boxes that you can see here. One is a laminar soil shear box. You see the frame can move relative to each other. So when we shake it at the base, the soil, you can have vertically propagating shear waves in the soil. This is a much more stiff box here. You see the dimension of this box, very large. It allows us to investigate the seismic response of soil foundation structural systems. It is it's a very complementary tool to the centrifuge machine, for example, at UC Davis, to validate computational models. We can also study soil liquefaction by putting a liner inside the box to contain the fluid and saturate the soil inside the box. And here, I'm going to show you a short movie from one of the tests performed by Professor El Gamal. You see the construction of the laminar box here. It takes about a week to set it up. And you see the installation of a single pile in the box and the filling of the box with multiple layers of soil. And here you see a snapshot of the box during a test. Notice that there is a ramp. I'm not an expert in geotechnical earthquake engineering, but I know that soil liquefaction is accentuated if there is a slope in the terrain, and the soil spreading due to soil liquefaction will be accentuated. And so here you are going to see two movies in parallel here. So look at the response of the shear box. You will see a little leak of water at some point, and you will see that there is a layer about here that is much more vulnerable to liquefaction than the rest. So you will have a shear strain much larger. You already see it here because that picture is from the middle of the test. So the layer here has very large strain due to soil liquefaction. And then you will see here the lateral soil spreading, gradual migration of the soil to the right and of the pile as well. See the water leak here. Okay, here we see a retaining wall with the reinforced earth. Professor Patrick Fox, when he was here, so there was a lot of instrumentation, accelerometers in the soil, strain gauges in the synthetic material. So you see a test here. You see string potentiometers to measure the displacement. You see the result of the string potentiometers here, the accelerometers here. And here you see in white, the acceleration of the table, and in red, the accelerometer that is at the crest of the wall. So a very large amplification. And you see some significant crack in the soil here. And one more test about soil foundation structure interaction. The California Department of Transportation is very interested in designing bridge with column on foundation that rock on the soil. So to speak, to push the nonlinearity at the interface of the foundation and the soil and out of the structure. So here we're going to see two specimens, one that was rotated 45 degrees, two columns with a very large tributary mass at the top. Inside the large box that we have, all this outrigger is to prevent the column from tilting and damaging the box, right? So it's not part of the specimen, but you can see here. See, with our camera, we can have amazing shots that speak more than many, many sensors. We also have a staging facility that is even larger than the footprint of the platen. The platen is 40 feet by 25 feet here, 44 feet by 30 feet, 3 feet deep. So this is for building maybe specimen up to 100 ton, and then they could, with a crane, be moved to the platen to increase the workflow at the facility, the throughput of the facility, or to build big component of a very large specimen and then bring the component on the platen. A few words about hybrid shake table testing. We have some basic capabilities in terms of hardware and software. You can see them here. And I'm showing two cartoons, so to speak, here. One where you would have a tall building and the top few stories would be used as a tune mass damper and connected to the remainder of the building through some devices, passive, semi-active or active. And then, for example, in a case like this, we could test these top few stories on the shake table platen with the devices. And then the bottom part of the building would be modeled in the computer. And using hybrid testing at every time step, we would measure the force feedback from this part onto the platen and bring this information into the equation of motion in the computer and combine it with the equation of motion of the bottom part, and then predict the response of the complete system at the next time step. And then we would have at the next time step, the displacement. Here, we would command this displacement on the shake table. So at the difference of using a shake table when you give the complete signal at the beginning of a test, here you would send to the shake table controller one value at a time, so in real time. And here we would, for example, be interested in a building with a stiff mat foundation on the group of piles. So the pile and the surrounding soil would be modeled, for example, in the computer, and the building on the shake table. And at every time step, we would command the total foundation motion to the shake table. Regarding this, a few years ago, my colleague, Professor Gilberto Mosqueda, did some commissioning test about hybrid shake table testing. Basically, he did this at a reduced scale. And he has a paper or two published about this and a report if you're interested. Whenever we test, we have a lot of dissemination of the test results and the tests themselves. We have a team in the Jacobs School of Engineering, media relation, that would put the researcher in contact with the various news media. And you can see here, it goes through TV channels and newspapers at the national and international level. So now let's talk about the upgrade to 6 degrees of freedom. So here, what we have seen so far, right? We have the 1 degree of freedom table here. From 2004 to 2009, we had just pressure balance bearings. That's it. 2009, we brought 6 vertical actuators, but non-ported, so could not be used dynamically. And then you can see here, all of this is the picture of the 1 degree of freedom, right? The hydraulic power supply. You have seen the accumulator bank, the 2 pumps. We have 1 pressure line, 12-inch diameter steel pipe. And then when you are in the reaction mass, it becomes 8-inch diameter pipe, one going to the west actuator, one to the east. And then the blue pipe is the return flow. So now the idea that we already had in 2004, 2002, and that slide comes from 2002. You see, it was before we trimmed the corners here of the reaction mass to lower the cost. So this was the idea, to have V-shaped horizontal actuator and add one hold-down strut in the middle and double. At the time, we thought doubling up the accumulator bank would do it. When we started to do accurate calculation, we realized we need to multiply by 4 the accumulator bank. So this is now the new hydraulic power system. Again, like I said, remove the existing accumulator bank and have one that is not 2,500 gallon, but 10,000 gallon. Very different type of accumulator bank. Tomorrow you will see it in the virtual tour. It's very impressive, incredibly tall bottles. And we had to acquire 2 more pumps to pressurize the accumulator bank. So we have 3 pumps that pressurize the accumulator bank at 5,000 PSI and 1 pump that is used as a pilot flow, to provide the pilot flow. Okay, so just checking here the time. Yeah, all right. So you can see here a few things. We have to double up the number of pressure lines. We need 2 now, 12-inch. When we are in the pit, we have a complete ring. We have to feed every of the 6 vertical actuators. So we have a pressure main ring and then a pressure main return. You see here a few nice renderings showing the pressure line here and how with this manifold it feeds every vertical actuator now, and then you have the return line in blue. You see the V-shape actuators. You see the vertical actuators ported now, each of them with a very large servo valve. You see one here. You see the base plate for the horizontal actuator. We are in the process actually, as we speak, to install those, post-tension them to the reaction mass. And we have also these plates here that are impact plate for the crash protection system that I will say a few words about. So you see here the vertical actuator and the new servo valve, 5,000 GPM. Very, very high flow because of the large cross-section area of the vertical actuator. You see here that we need to bring that 3rd hold-down strut here in the middle. Everything was ready for it. We just needed to order from the same supplier, the same one as the other 2. You have a lot of inline accumulation here. You see here as well. And here you see that we will have bumpers. You see these bumpers, one at each corner, call it crash protection system. You probably wonder why. This slide should explain it to you. In the transversal direction here, the clearance is 50-inch here, but here to unseat the vertical actuator 17-inch, and here to start to impact with the belly of the platen, you know, the wall here of the reaction mass, 34 inches. The V-shape actuator of the upgrade is capable of moving the platen 42 inches in that direction. So you can see it's more than the 34 here. Not quite as much as the 50, but if you put 42 inches and the maximum yaw, you can touch, you can impact that part with the platen. So in order to prevent this from happening, we have 3 lines of defense. The first one is to program the limit in the controller. And if this does not work, we also have physical limit switches that communicate with the controller of the shake table for aborting the test in case there is you know, these limits are detected. And then if these 2 do not work, then we need to absorb the crash without damaging the reaction mass. And this was designed, you know, these bumpers here, each of them you can see has 42 rods. Here, when you have an impact, you push on the middle part here, it puts the rods in tension, it yields them. And we wanted, the design criteria was to stop a specimen of 1,000 ton moving and impacting the reaction mass at 1 meter per second, to stop it with 2-inch displacement. So since we had 17 inches, right, we want to allow only 15-inch of displacement for testing, because from 15 to 17, this is to absorb the impact if we have to. So now you see here the uni-axial performance characteristics, and you can see that now we will have plus or minus 89 centimeters in the longitudinal direction. It's counterintuitive, but if you look at the trigonometry, you have to divide by the cosine of the angle and not multiply. So 89 centimeters, horizontal plus or minus 15 inches, I just explained to you, 38 centimeters, vertically plus or minus 5 inches. The peak velocity, we had 1.8 meter per second. We are going to reach 2.5 meter per second in the X direction, 2 meter per second in the Y, 0.6 meter per second in the vertical. Remember, 6.8 meganewton was the peak horizontal force for the 1 degree of freedom, 6.8. We are now exceeding 6.8 in the transversal, 838, and 10.6 meganewton in the longitudinal. And then the peak rotation, 2.2 degrees, 1.5. So this is the roll, plus or minus 2.2 degrees. The horizontal, so this is the pitch, plus or minus 1.5 degrees. And then the yaw, plus or minus 4 degrees. This seems small to you, but there has not been many measurement or large of near fault rotational ground motion. But people have simulated them using elastodynamics and so on, and a few degrees is very, very large for ground rotation. And then here you have the overturning moment capacity and so on. So we also, we are in the process of the upgrade. We used, MTS has a model of shake table that they can customize to every shake table. So we worked with them to customize it to our upgrade and to calibrate the parameters and put the best possible parameters. And we tried here is to show you, we tried to simulate in advance how well the upgraded shake table will be able to reproduce earthquake ground motion. This is the Chi-Chi Taiwan earthquake. You can see the target in red, the real earthquake record in red, and the one that we predict will be reproduced by the 6 degree of freedom LHPOST. So it's very promising. You can see it remains an accurate table. Of course, we will have to wait until the commissioning test to see, you know, if this model there is uncertainty, of course, about the prediction of the model. This is what we think the velocity, how it will be reproduced in the 3 direction, X, Y, Z, the vertical here. Again, you see, very good. And this is for the reproduction of the displacement. So I want to talk also about, I can see that, yeah, I still have time. Modular test bed building. Right, so we have here basically a large-scale testbed building that will be available as a shared use equipment. It will enable low-cost testing of component and systems, since researchers will not have to, you know, reserve fund to build the building. So it's a building that will be reconfigurable. It's full scale here. You can see it's the length 32 feet, width 20 feet, height 36 feet. It will allow to, you know, for example, test seismic protective system, lateral force resisting system, non-structural components, and so on. And it has very interesting features. You see, every floor can be built as a moment frame or as a brace frame. And you have a number of devices that are replaceable, that are the device where the nonlinearity will be concentrated, like, for example, buckling restraint braces or special moment frame joints, shear fuses. So for repeatable nonlinear behavior. So this was designed and by our 2 colleagues, Professor Gilberto Mosqueda, Tara Hutchinson, and Professor Chris Pantelides from the University of Utah. It will become available by the time we reopen for 6 degrees of freedom. It will be available. Now, new research opportunities made possible by the LHPOS 6. I have just 4 slides now to conclude this presentation. So I try to summarize here a number of topics, and maybe this would be also a good starting point for the breakout session tomorrow. So we will be able to study the response behavior of large-scale specimen in 3D at large or full scale again, under the combined effect of not only the 3 translational ground motion, but also the rotational ground motion, which traditionally have always been neglected for 2 reasons: because they are not measured, they've not been measured in the past during real earthquake. Now they start to measure them, and the field of rotational ground motion seismology is a very, very fast evolving field right now. And the second reason is that the seismological community assume that they are negligible. But there are a number of papers in the literature that have shown that there are certain structures, tall building and tall bridge towers, that could be very sensitive to rotational ground motion component, like the cartoon here showed by Professor Trifjunak from USC in a paper in 2009. Right, you see the cartoon here. If you shake this building in the horizontal direction, you're going to have drift of the building just due to the horizontal excitation. Now, if you rotate the base, in the case you have the passage of a Rayleigh wave, you just rotate the base back and forth, you also have drift, and these 2 drifts can add up. And so we'll be able to do all of this for structural, geotechnical, and soil foundation structural system, including the effect of soil structure interaction, kinematic, inertial, and nonlinear soil and structural behavior and soil liquefaction. Another important topic is inherent damping in structures. You know, what is a realistic model to use in simulation for damping? It's a topic where there is no consensus yet. So to do some targeted experiments with 6 degrees of freedom excitation should be able to bring some light into this topic and some guidance into what kind of damping model used for numerical simulation. Experimental study of dynamic soil structure interaction, kinematic interaction, and inertial interaction. 3 types of experiment will be able to be performed. One of them, researchers will model a system, including the structure, the foundation, the soil in the computer, do a state-of-the-art simulation, and we'll get from that simulation the total foundation motion, including the translation, the 3 of them, and the 3 rotation. And then we will play on the platen these total foundation motion and put only the building, let's say, on the platen, and compare the response of the building to the one that was purely simulated numerically. Or some hybrid test, like I talked about before, where the superstructure will be on the table and the soil will be modeled in the computer. Or using the large soil boxes, where we will build a specimen of the foundation and the superstructure at reduced scale, still large scale, and put it embedded in the soil box, and then shake the soil box at the base with either tri-axial or 6-axial excitation. In terms of real-time hybrid shaking table testing, there will be room to expand on the complexity of large-scale tests that can be done in a hybrid way. This is a delicate topic because the risk of impact between the platen and the reaction mass and damaging, the facility when we debug the hybrid algorithm. So that will be a delicate issue, but of course there is tremendous room for developing hybrid testing at large scale. And then if you consider unreinforced masonry buildings, walls of such types are subjected, when subjected to uni-axial in-plane forces, of course, tend to exhibit a much better performance than if you put biaxial horizontal excitation, right? And you have experience out of plane collapse. What about if we bring the vertical ground acceleration into the picture? Also, this could have play a big role. And for reinforced concrete and reinforced masonry structures, many of the design provisions are based primarily on in-plane horizontal loading test of these components. Again, here, when you have bi-horizontal excitation and vertical, it could change the results quite a bit. So multi-axial shake table tests are needed to investigate this problem and improve further the current design codes. And the last slide here, for non-structural component and systems that represent a very large value in tall buildings. For example, it's important to improve our understanding of the seismic response of these systems under multi-directional earthquake excitation so that a reliable unified design methodology can be developed for these systems. And now there is a trend for going into low damage, or in the extreme, right, damage-free, maintenance-free earthquake protective system, such as self-centering system, rocking, accelerated bridge construction. These systems have a pretty complex kinematics, and a lot of them have been tested in uni-axial behavior. It's important to test them in more realistic multi-directional earthquake input. Here, just to show you, after we reopen, we will first test the reconfigurable test frame building that I talked about for 2 weeks, just as a guinea pig also for the new system. And then we will have this full-scale 10-story timber structure made out of cross-laminated timber and rocking walls. I think Professor van der Lind will probably talk more about it. So this is will be a very exciting test to start with. You see a rendering of this test here. And thank you very much for your attention. Here I have listed, if some of you want to contact people from our team, you have the email and phone number. Sorry, not phone number, but email. And this concludes my presentation. Thank you very much for your attention.